So we want to talk about stacks and queues. Woo! Exciting times. Stack and queue, but first we got to talk about deleting a node. Oh, this mic is so high up. All right, but first we want to delete a node. So how are we going to delete a node from a linked list? These slides, I never get to them. They're in Wednesday's content, but I never get to those slides, so I just put them on the beginning of these ones because I know I'm never going to get them on Wednesday, get to it on Wednesday. And this is really important for your homework because that's the biggest thing I ask you to do on task 3 is deleting a node. You have a song with a linked list of ratings, and you have to delete a rating by a reviewer, given a reviewer, getting their reviewer ID, and then removing the first rating with that ID. So we got to talk about deleting a node since that's the big thing that we ask you to do on the homework. And stack and queue, we really don't ask you to use on the homework at all until task 8. But even then on task 8, I'm fine if you use Java's built-in queue. So anyway, stack and queue will be interview questions though. Deleting a node. So say we want to delete a node. I've kind of mentioned it before that what we'll do is manipulate the references to be able to delete a node. So let's put that into visual form and see how we're going to delete them. And in this example, let's say we want to delete the node with the value 2. To delete a node, we're going to need a reference to the node that comes before that node. That's how we need that information to be able to get this to work properly. And what we're going to do to delete that node is this. We're going to update next of the previous node to the next of the node we're deleting. Which I think I got that one right. So we're at this node and we want to delete the node after it. We're going to set its next. So say we're in a stack frame where this is a reference to this node. We would say this.next equals this.next.next. Or get next if we're using the getters. If we're inside that linked list node class, we don't have to use the getters. So we're going to update next to the next node. We're effectively cutting that node with the value 2 out of the linked list. And now this linked list, if I have a reference to this node and thinking of that as my linked list, then this linked list is now 4, 3, 1, end of list. We effectively cut 2 completely out of this linked list. And that's it. We updated one reference, and that's how we can delete a node anywhere in a linked list. So as opposed to array list, where if we remove a node, everything that comes after that node, we have to shift over one in memory. There's a lot of work to do deleting from an array list. But since a linked list is all over memory and only linked together using these next references, we update the reference, one single reference, and we deleted a node. That's it. And notice that we don't actually delete the node. The node's still hanging out there in memory, but if we don't have a reference to that node anywhere else in memory, it's a candidate for garbage collection, and Java's going to clean up our mess for us. So we remove the reference to that node, and then that's it. Java does the rest for us. We don't have to really worry about anything else. That's deleting a node. That's really all I have to say about it. So in relation to our homework, I'll say a little bit more about it in relation to the homework. When you're trying to delete a node, you're going to, this one's a little bit trickier to set up because you're going to need a reference to the node that comes before the node you're going to delete. So you're going to go through the linked list of ratings and keep track of 2 different nodes, the node you're currently considering for deletion and the node that comes right before it. So once you find a node that you're going to delete, you say, oh, this node has the reviewer ID that I want to delete. Then you go to the node that comes before it and start updating the references. And there's a couple of edge cases for this one. By the way, deleting a node is by far the hardest part of the homework. I don't think it's overall too difficult of a homework. Some of you will end up disagreeing with that, but also you haven't seen tasks 5 through 8 yet. So it's not overly difficult, but by far the most difficult part of task 3 is deleting a node. You got to keep track of the 2 references and the 2 edge cases. are what if the node you're deleting is the last node in the list? Make sure you're handling that case. And what happens when the node you're deleting is the first node in the list, and handling that case as well. So a bit to keep track of, a bit to think about. It's a bit tougher algorithm than the 4 we covered on Wednesday, which is what we expect. Take the concepts of those, understand how to do those, and then start combining that with the rest of your programming knowledge to be able to introduce this new concept into your arsenal. That's what we want you to be able to do. So any questions on deleting a node? I see a few things in chat. Let me catch up. How would you go about finding the node before the node we want to delete? We use recursion. Well, I would use recursion. However you do it, that's up to you. I use recursion. My solution, I use recursion. If you are, I'll give a hint since it was asked for. If current equals target, delete, else current dot next. I mean, stronger than that anyway. If you're going through the nodes, I would think of the node that I'm currently visiting is the node before the one that I might delete. And then whenever I'm checking a node, I have a reference to the node that's before the one I want to delete. I'm going to check that node's .getNext, .getValue, .getReviewerID. That's what I'm actually checking for deletion. So I'm not really tracking 2 nodes simultaneously. I'm tracking 1 node, but the node I'm tracking is the one that's before the one I'm considering for deletion. So as long as next isn't null, I'm going to check next's value to see if I want to delete that one. And if I do want to delete it, then I delete it right there. So I'm really only storing 1 node in memory, and I'm checking its next. I'm never saying the node.getValue, because I don't care about the node's value of the node that I'm currently visiting. I care about the next node's value. And I want to see if I want to delete that one. But don't move on from that node, and don't move on from a node unless you know that the node after that one is not one that you're going to delete. I think that's a fair hint. Do we need a reference to the node after we are deleting as well? The node after the one you're deleting? I mean, technically, yes. After the one we are deleting is technically yes, because you have to set the next. So this is the node we're currently visiting. This is the node that was a candidate for deletion. And this is the node after that one, to put a visual on what we're talking about. This is the node that I currently have in memory. I have some variable named node, and this is the reference that it's storing. And I'm going to say, is the next node, this next node value, is this a value that I want to delete? For the purposes on the homework, it'll be a rating. You'll get its reviewer ID and check to see if that's one we want to delete. If it is, then this next needs to have a reference to this node. So the node we're deleting's next reference is a reference to this node. So we do need that reference because we need to set it, this variable, equal to this reference. So we will need it in that sense, but we don't need to store it in a variable in memory. So we don't need it in that sense, if that makes sense. How would you delete the first node? Deleting the first node is one of the edge cases. I'll leave this mostly up to you to figure out, but it's you would update the, I'll give a little bit of a hint for it. You need to update the instance variable in the song class. You need to update that to a new reference. You do the same idea, but you have to go, the node before the first node is the instance variable that stores the head node. Okay, any other questions on this? Stacks and queues. Stacks and queues. Stacks and queues. I think I want to, right from slide 1, put this out there. Stack and queue, the concept of a stack and the concept of a queue are very important. The actual code for these data structures, we will build a stack and we'll build a queue in today's lecture. We'll show you how to do that. But the actual code for a stack and the code for a queue is less useful. It's less important, in my opinion. It's kind of a hot take, I guess. But the code for them is less important. And I'll explain my thoughts on that as we go through. But what I want you all to take out of this lecture, and this is the reason why we don't have stack and queue in a coding task, but it will be on the interview, because the concept is what's important. I lost my sentence. But it's the concept of stack and queue that will be critically important throughout your computer science career, programming career, whatever you're doing moving forward in this technical space. It's going to be important to understand these two concepts, and it already has been important. The memory stack is a stack. It's right in the name. Memory stack is a stack of stack frames. So it is very important that you understand the concepts. But coding, I think the code's pointless. But actually, I can say that right on this slide. So we're going to build a stack and a queue from a linked list. My counterpoint to doing that is, why not just use a linked list as a stack and as a queue? If you understand what stacks and queues are in concept, you can take a linked list and just use it as a stack or a queue, and just be careful about how you're doing, what you're doing with it. What a stack and queue actually does in the code is restricts your operations that you can do, restricts the methods you can call on these data structures, on the underlying linked list, to only the stack or queue methods, which are very efficient methods. They're all, as we're going to see, are O of 1 methods. But what if you want to use one of the more expensive, more inefficient operations? You just can't. But if you use a linked list as a stack or a linked list as a queue, more likely stack. We'll get into it all. But if you use a linked list as one of these data structures and just only use the O of 1 operations, and then if you decide, what I'd really like to do is ask this stack for its size, which is something a stack can't do. If you have a linked list, you just ask the linked list for its size and say, okay, I understand that this is a slower operation, and I'm okay with that. So with that preface, let's talk about what these things actually are. A stack in the real world, hopefully you know what the word stack is. I always think of like a stack of papers or a stack of folders like this. It's a last in, first out, or first in, last out. Both acronyms mean the same thing. Data structure, meaning that whatever I put on top of the stack, if I want to remove something from the stack, that's the only one that I can remove. This is exactly how our memory stack works. We have a main stack frame that we place on the stack, and if main calls another method, we put another stack frame for that method on top of main, and it's only the stack frame on top of the stack that can be removed, and I can only add more stack frames on top of that. So I can have a stack of stack frames, but it's only the top stack frame that's the active stack frame. Variables in that stack frame are the only ones that are accessible at any given time, only the top of the stack. And I can only remove that stack frame and go to the one that's directly underneath it. That's how our program operates. That's how our method calls maintain their organization. It is a literal stack. It's a last in, first out data structure. It's a stack of stack frames in memory. Stack has two methods, and that's it. It's push and pop. Unrelated to stack and queue, this is a stack and queue lecture. But there's a difference between updating. Is there a difference between updating the instance variables representing the current node versus updating the variable created in a method that's assigned to the current node? Oh, I got to wrap my head around this one. Is there a difference between updating the instance variables or modifying the variables that are, I assume you mean in the stack frame, representing the current node versus updating the variable created in the method that's assigned to the current node? Not 100% what you're saying, so I'll take a stab at it anyway. The instance variables, I think you're saying, is there a difference between changing the instance variables or changing the variables in the stack? There is a difference, no matter what interpretation I take of this. Maybe you mean, or updating the reference. So you have a variable storing a reference to a song. Is there a difference between changing the instance variables of that object or changing the reference stored in that variable? Maybe that's what you're getting at. I'll let you clarify. But yes, there is a big difference in either case. Like if you say new song, create a new object on the heap and replace the reference, it's a new variable, and you have the old object, which may be garbage collected if you don't have any other references to that object in the heap. And if you do have two variables that are referring to that same song object, and you change the instance variables, that change can be seen from both references. So that would be the practical difference. The first difference would be a more technical one if there's only one reference to that object. It's a space inefficiency thing. You're using up heap space and relying on garbage collection. It can slow down your program if you abuse that too much. And the second one is an actual functionality difference. Your code will do something different because now you changed, song 1, song 2 is two different variables. Song 2.set title is going to change the title of song 1, whereas song 2 equals new song isn't going to affect song 1. That's my interpretation of your question. If I'm off, send a follow-up. So 2 stack methods, push and pop. Push, add something to the top of the stack. Pop, pop something off of the top of the stack. And that's it. 2 methods. 2 methods. That's all. Certain implementations of a stack will often give you a third one. We like peak or top is what it's usually called, where you can return a reference to the top of the stack, the element that's on top of the stack, without removing it. But that's not part of a stack in concept. The concept of a stack is only push and pop. If you want to see what's on top of the stack, you pop it. You pop it, that removes it and returns a reference. And now you have the top element. If you decide you just wanted to look at it, you would push it back on top of the stack, I guess. But this is all a stack needs to be a stack in the land of theory. In the land of code, usually we have that third method just because it's useful for a lot of our applications. And that's it. And that's why I don't like stack. Like, just use a linked list as a stack. Then you have all of your linked list methods. Stack, this is it. Notice what's not on there. Size, toString, append. You just can't use those methods. So you're artificially restricting yourself to these 2 methods if you use a stack instead of a linked list. That's one of my pet peeves with these things. In code, when we used to teach this class in Scala, the Scala built-in stack class had a note in the comments of the source code for Scala said, I'm paraphrasing, but it said, why are you even using this? Just use a linked list, dummy. And I was happy when I saw that because I'm like, yes, somebody else out there agrees with me. Why would you ever use this? Just use a linked list. But anyway, the concept is what we're focusing on today because that is critically important. If you go to a job interview and they say, explain what a stack is, and you're like, I don't know, you should not get that job. And stacks and queues, really data structures and algorithms are what, for whatever reason, are what employers love to ask about in interviews. Stacks, queues, trees, graphs, a lot of the data structures we'll talk about this semester. For whatever reason, they're just fundamental CS stuff that interviewers like to ask about. So if for no other reason, you need to know the theory so you can answer those questions if they come up in job interviews. And luckily, stacks and queues are pretty straightforward. 2 methods. There's not much to keep track of. So here's some code that's going to create a stack and use the stack a little bit. I'm going to create a stack that's going to be empty. I'm going to push 1, push 2, push 3, and then pop. X is going to have the value 3, and that node with 3 is removed from the stack. So pushing to the top, popping from the top, we can only work from the top of a stack. And here's my class for a stack. So stack and queue, we're going to build both of them using a linked list. I'm abbreviating LL node for linked list node just to fit on the slide. Namely, this line right here was really cutting into my bullet points, so I changed it to linked list node or LL node instead of linked list node. But here's the class to do that, and let's go through this code. Oh, do I not? I got to add a slide for that. This is way too important. When we create a new stack, I have a linked list that's going to store that's going to store all the elements in the stack. And that linked list is initially empty. And I know I said this Wednesday for those of you paying attention. Sorry, I got to say this a few more times. But to represent an empty linked list, we're going to set that variable equal to null. This is a linked list. This.top equals null. Top is a reference to an empty linked list using the structure of the linked list that we're using in this course, where it's null terminated. Our stacks object. I don't know how to approach that. I have to explain like 3 weeks of content to answer that properly, but I'll just say no. Objects go in the heap. Stack frames go on the stack. And then we have references to objects on the heap on the stack. But we can chat more like after class or in office hours. I'd be happy to talk about it more. So this .top equals null is how we're storing an empty linked list in top. In your song class, you're going to have a linked list of ratings. When you first create a song class, it has no ratings. That ratings instance variable storing a linked list of ratings, set it equal to null. That's your empty linked list. That's how we're representing an empty linked list. The reason I stress this so much is I always see it, and I'll see it again this semester, especially from Paul's sections. I don't know if he's stressing this as much as I am. None of you are going to make this mistake, right? They'll say instead of null right here, they'll replace what's highlighted here with new linked list node of null null. And it drives me nuts every time I see it. I know I said this on Wednesday, but it's something that I see every semester, and it's a complete misunderstanding of what we're doing whenever I see that. So I want to squash that misunderstanding right now. New linked list node of null null is a linked list of size 1 that stores the value null. It is not an empty linked list. And when you do that, what you're going to get is null pointer exceptions all over the place, because now you're calling .getReviewerID on null, which is going to give you a null pointer exception every single time. Then you're going to say, why am I getting null pointer exceptions? What is going on here? It's because you're not setting this to null. You're setting it to a linked list of size 1 that has the value null. Yep. Nope. I don't, except for nulls like that actually have meaning like this, that's not something I throw at you. Because I could throw that at you right from task 1, your average method, what happens when I pass null into it. I just don't touch those edge cases. It's just something like, you would have to add that to like every single method that you test, and I don't know, it's just, I don't see much educational value in adding that to absolutely everything. So I just don't. Maybe I should. I don't know. Maybe there is value. But this semester, I'm not doing that. For sure. How do you make an empty linked list? Oh, my God. I have to say it even more. Why does the stack class have a return type? This is how you create an empty linked list. This is it. Set your variable that stores a linked list, set it equal to null. That's an empty linked list. Why does the stack class take a variable? That's a type parameter. We talked about those Wednesday. Stack takes a type parameter, so I can create a stack of any type. And you specify that type when you create a new linked list, or a new stack. Same as if I create a new array list, I say array list of integer. The array list class says the same thing. It's array list of whatever variable name they chose for the type parameter. Okay, and let's go through our 2 methods. Push, this is just prepend. So this is the first time we created a linked list. We would create a new linked list node and then set our head of our list, set next of the new node to the head of the old list, the old head of the list. So I've effectively prepended this node, this value. I'm creating a new node with this value, and next is whatever the old value is. So if this .top is a reference to a linked list of 1,000,000 elements, I just prepended this new value to the beginning of that linked list. If this .top is null, I just created a linked list of size 1 with that value in it. Whether top is null or not, doesn't matter. This is going to create a new node that's prepended to the beginning of that list. And then update my instance variable to be a reference to the new node. And I could, for what it's worth, I could do this in one line. This .top equals new linked list node. That would work as well, instead of using this temp variable. I think the temp variable was for memory diagram purposes at some point, if I recall. I don't know why we use a temp variable there. I don't know. We don't really need to. And then pop. This is one of our first, aside from our knowing when to stop our recursion checks, this is one of our first null checks that we have to make. Null checks are going to be critically important right from the testing utilities, the first thing you'll do on task 3, you're going to need null checks aplenty to make sure what you're checking isn't null. Since null does have meaning when we're working with linked lists, when null has meaning and it's part of our intended use of the class, that's where we will have to make our null checks. I won't throw the crazy edge cases of anything could be null except primitives, but these we do have to do. So if top is null, popping is going to do something different than if top is not null. So if I try to pop off an empty stack, it's actually a good question of what should we do? I'm just returning null here. What actually happens in most stack implementations is it throws an exception and can crash your program entirely. You're just not supposed to pop off of an empty stack. If top is not null, so we're going to have separate cases for each of these, and to start our recursions, is the list empty or not? For your testing utility, are these lists 2 different sizes is going to be the big thing. So I'm comparing these 2 lists. One of them might have a next of null, and the other one might have a next of an actual node. So checking to see if one of them ended before the other one is going to be an important check to make on that testing utility. So checking for null in a lot of different cases. If the top is not null, the head of the linked list is not null, then we're going to get the value. This temp we do need. We're going to set top to next, next. By the way, the question of how do we remove the first element in a linked list, we're kind of doing exactly that in our stack right here. Not to give it away, but you update the instance variable that's referring to the list. So this refers to the head of the list. The head of the list is now the second element instead of the first. So we just cut out the first element out of the equation entirely. And then we're going to return temp. This is why we need the temp variable, because after this line executes, we no longer have access to the head node. So we need to grab the head node's value before we get rid of it completely and send it to the garbage collector, and then we can return that value after the fact. So that temp variable is very, very much necessary. Any questions on the implementation here? Let me catch up on chat. Oh, why does class have a return type? I read that wrong. I don't know where you're seeing a return type. That class have a return type? I don't see a return type. Unless you mean here? So stacks are stored in the heap rather than on the stack. Oh, yeah, that is confusing. Yeah, stacks are stored in the heap. Oh, goodness. I never thought of it that way. Yeah, stacks are stored in the heap, though, because our stack is going to be an object, so that object is in the heap. So the memory stack applies the stack concept of first in, last out, or last in, first out. But it has nothing to do with this stack that we're talking about here. This is a stack that's going to be an object that lives in the heap that has a reference to another object in the heap, which is a linked list, which can have a reference to an object, etc. So yeah, it does get a little trippy when you word it like that. How many stacks can a stack stack if a stack could stack stacks? A lot. Fit in memory, I guess. Why exactly do we want to make new linked list nodes every time we push? Because we're using a linked list to represent our stack. So every time we add an element to a linked list, we need to create a new node for that, element. That's how our linked lists work. That's our linked list structure. Okay. Let's go through this with what I call an abbreviated memory diagram. We already did one of these on Wednesday, but I'm going to do some of my memory diagrams in more diagram fashion. At this point, I make an assumption that you can create objects on the heap, constructor calls, manage your references and stuff. There's no new memory diagram concepts for linked lists, and I think we wouldn't do this, but I think it would be decently fair to give you the linked list memory diagram quiz right after your classes week, because we don't learn any new memory diagram concepts when we cover linked lists. It's just applications of what we've already done. So I can skimp on the memory diagrams a little bit this week. I did the one on Monday. I did update the slides yesterday to have the finished memory diagram in the slides, so you can check that out. Or watch Paul's lecture. He does the memory diagrams every lecture. So I am going to do more visual style, and then you can know that this will be 3 objects on the heap. They'll all have OX whatever numbers, and these will be instance variables with those values. But I want to abbreviate them because I have like 3, 2, I don't know. I got a bunch of them to go through today, and if I did full memory diagrams, we would never get through the first one. So pushing to a stack, we're going to run this code. Pushing 3, we create an empty stack where top is a reference to this. Wait, where top with a Q, I go through it step by step. But stack has an instance variable top with a reference to null. We're going to push 3. That's going to set top equal to a new node with the value 3 and next equal to the old top. So top references this node. Push 7, update top to a new node with the value 7 and next equal to the old top. Push 2, update top to be a reference to a new node with value 2 and next equal to the old top. So we pushed 3 values into the stack, and this is what our stack looks like. It is a linked list. It has a reference to a linked list, and that's how we're representing our stack in memory. But we think of this as a stack data structure because we wrote 2 methods called push and pop, and they do what we expect them to do. And then we want to push -5. When we push -5, we're doing the same thing. Create a new node. Its next is a reference to the old top of the stack, and update top to a reference to the new node with the new value. And what I want to point out with this is the old linked list didn't change at all. When we prepended to this list, the old list doesn't actually know that anything happened. Nothing at all changed inside this box. It's completely unchanged. All we did was create a new node that has a reference to that list. But nothing actually changed with that list. And same when I pop -5, I don't update what's in the red box. The red box didn't change at all when I pushed and popped 5, which can make these things very efficient. I think that's where I want to cap that conversation. It makes the linked list able to be immutable, which used to be a big topic when we taught this in Scala, but less important now. But when we pop, top gets updated to the next value, and we return -5, we still didn't change that portion of the linked list. Then garbage collect that node if we don't have a reference anywhere else in memory to it. What's the difference between push and append? Append adds to the end of the list. Push is going to be the same as prepend, which adds to the beginning of the list. And stacks are very efficient. Oh yeah, I guess that's why I can still talk about the red box. Both these operations, I guess the constructor too, are what we call O of 1 operations. A lot of the runtime talk I'll save for 250. I'll let them talk about it. They'll talk about it all semester till you're sick of hearing about it. But I will talk about it a little bit in this lecture. These are O of 1 operations, meaning they're constant time, which means these operations take the same amount of time no matter how many elements there are in the linked list. When we push or pop, we're not even touching the entire linked list. All we did was change what the head of the list is. We only affected one single node in this list. So it doesn't matter, So it doesn't matter if the stack has a billion elements, or 2 elements. It's going to have the same runtime to push and pop. And this is why we like stacks. This is why there are data structures in code that exist like this that restrict you to push and pop, because it forces you to only use O of 1 operations. And the only protection it's really given you, the reason I don't like them, is saying if you're going to be a very sloppy programmer and not think about what you're doing, we're just not going to let you do anything that's too inefficient. We're not going to let you ask the stack for its size because that's an O of n operation. So we're actually going to not let you do that. Instead, you should just be a better developer. And if you are concerned about runtime, if you know your stack is going to have billions of elements, don't ask it for its size. Just don't do that if the runtime is that important. I mean, if runtime's not that important, just ask it for its size. Who cares? But if runtime is that important, just don't do that. Don't artificially restrict yourself to just push and pop by using this data structure instead of using a linked list and using prepend and updating the reference to remove. You could write push and pop just like we did as a linked list instead of writing a separate class. Because notice I don't have access to the linked list. The way I wrote this and the way stack is supposed to work is you can't access the linked list. There's no get top method here that would let you get a reference to the linked list and do whatever linked list stuff you want to it. We don't have that functionality with a true stack because that would be inefficient. So why artificially restrict yourself when you can just use a linked list properly and sanely and just avoid the expensive operations when it's important to avoid them? So that's my take. I'll stop that rant. But all these things, they're all O of n. O of n means it depends on the size of the list. If you call toString size or find or append or find when the element you're looking for isn't in the list, what you have to do is bounce all around memory, visiting every single node in the linked list before you know that before you get to the end of that algorithm. So where n is the number of elements in the linked list, it's going to be a runtime of the order of the number of elements that are in the list. So very slow operations if you have very large linked lists. And stack says, no, we're not even going to let you touch those methods. Very self-deprecating to use an actual stack, in my opinion. Push and pop need to be generic, or are they only generic in this example? They only generic for this example. Like the concept of a stack doesn't care what it's a stack of. If you write a stack of int as a class and it only works for ints, you still got yourself a stack. So the concept doesn't care. But the code, I mean, if you're coding a stack class, you should probably make it generic because then when you want a stack of strings later on in the future, you don't have to write stack of strings, and then stack of doubles. You don't want to write a class for every single one. Stack of ratings, stack of songs. That size is O of 1, not O of n. I disagree strongly. Size can be O of 1 in specific implementations if you keep track of the size independently. So as was pointed out on Wednesday, when the Java stack linked list class does independently track its own size, then it can just return the value of that instance variable. But if you want to compute the size and you don't already, I mean, if you already know the size, it's O of 1. Yes, of course. But if you don't already know the size of a linked list, it takes O of n to compute that size. In Java-specific implementation, it can be done in O of 1 because it's doing extra work elsewhere, which is optimal, actually, the way they do it, is keeping track of that. Doesn't add to the runtime. The asymptotic runtime anyway. But if you're not tracking it, it's O of n, baby. All right, so Q is going to be kind of the other side of this, the first in, first out, or last in, last out, if you want to say it the other way around. And it's a typical queue. You queue up in line. Whoever's in front, who's been there the longest, they're the next one to go. Concept, hopefully, at that level, we're all good with. Just waiting in any line that you've ever seen, that's a queue. You queue up in the line, queue up to the end, and you wait till you get to the front. Our methods, we have two methods, just like a stack, enqueue and dequeue. The big difference is enqueue is going to add to the end of the linked list, effectively append, and then dequeue is going to remove from the front of the linked list, same way as we did with a stack. So enqueue and dequeue, the usage here, we create an empty queue. We're going to enqueue one. Hey, my mic's on. False alarm. They'll call if my mic's out, but my mic's fine. They'll enqueue one. Enqueue two, we're adding at the back of the queue. Dequeue, we're dequeuing from the front. X is going to store the value 1, and 1 is removed. So we remove and return. And here it is. There's all the code. So this code is a little bit more than a stack, but we're really not doing much more. The big difference is since we're working from both the front and back of a linked list, we're going to store references to both the front and back. And here's where I will go back on what I said a little bit. If I need a queue, sometimes I do use a built-in queue implementation. I'll use Java's queue from time to time. Because of this extra bookkeeping, sometimes I just don't feel like doing this with a linked list, so I'll just use the queue class. So I do back up a little bit on that. With a stack, it's easy enough to use a linked list as a stack, so I'm just going to use a raw linked list for that. But with this, that's extra bookkeeping, extra work that I don't always feel like doing. But it's out of laziness, not out of what I should be doing, for what it's worth. So since we have to work at both ends, and working at the back of the linked list can be O of n if we're not careful, because you need O of n just to get to the back and then do whatever you're doing. So if we store a reference to the back, now we don't have to do that. We're always at the front and back of the linked list at all times. I don't have to navigate to the back every time I want to in-queue something. Set them both to null. They're both empty linked lists. And when we in-queue, if the back is null, so we have to do a little bit of extra work here. We do have to care if the linked list is null. If the linked list is null, create a new linked list with the value and next of null. Set that equal to the back and the front. If we have a queue of size 1, that one element is both the back and front of the line. If you're the only one standing in line, you are the front and back of that line. So front and back are both equal to the same node that we just created, that single node. Otherwise, we don't care about the front. We just want to in-queue in the back. So back, we're going to set back's next equal to a new linked list node that we're creating. So we're adding this to the back and appending it to the list. And then updating back to be a reference to that new node that we just created. I think I'm getting ahead of my slides here. Yep, I'm getting ahead of my slides. I said all this, but my slide wasn't on board with me. So when we have that reference back, this in-queuing is O of 1 because we're already at the back of the list. And then we're going to update that reference to make sure it's always at the back of the list. And then dequeue, again, a little bit of extra bookkeeping here, but not too much. If the list is empty, or if the list is empty, return null. We can do something else there if we want, crash the program, throw an exception, return null, return, I guess that's our only real option is null. If the queue isn't empty, we're going to do the same thing that we did with a stack. We're going to get the value, store it in a temp variable, return that thing, and update front to be front's next. So we're cutting the first node out of the linked list. But we have one little extra piece of bookkeeping. If front is now null, we'll be in a case if front and back are both referencing the same node because there's only one node in the list, and we get rid of front, and front is now a reference to null, then back is still a reference to that old node that we just removed, and we want to make sure back is also a reference to null to indicate that this is an empty queue. So a little bit of extra bookkeeping to make sure front and back are both null when we dequeue the last element in the queue. So a little bit of extra bookkeeping than a stack, but pretty much the same concept. Yeah, the custom one's better. Don't use Java's built-in stuff. We're going to build everything from scratch. And let's do this diagram. So when we first create a queue, front and back are both referring to null. They have the lack of a reference. They're not referring to anything. We're going to in-queue 3. When we in-queue the first node, front and back are both referencing that same node. It is the front and back of the list, and that node's next is null because it's a list of size 1. When we in-queue 7, back is still going to be referring to, front is still going to be referring to that old node, the old head, but we're going to update back to be a reference to the new node that we append to the end of the linked list. And we're going to append 2. Back is going to be a reference to that new node 2. Front is still untouched. We don't do anything with front when we're in-queuing unless we're in-queuing into an empty queue. And then back is going to continuously update to whatever node we're adding. We're going to dequeue. When we dequeue, we're only concerned about front unless we're dequeuing the last element. So front is going to be a reference to the next node. We update the reference and then return the value of the node that was at the front of the queue. So X is going to have the value 3. We dequeue again, update front to the next node, return the value of the node that was in front. These two nodes will get garbage collected. Dequeue again. This is where we have the extra bookkeeping. We don't want back still referencing this node. We have to update back when we dequeue the last node in the queue. So front gets null, kind of automatically, the same way it did with a stack. But we have to check if front is now null, back has to be set to null also, because if back is referencing this node still, we're going to have some bugs. We're going to have some complications when we test that code. And then we dequeue again. What happens here? I kind of already mentioned this a few times, but what happens here? In our code that I showed on screen, this will return null. X will get null. Oh, actually, yeah, this does crash. X will get null, but since X is a primitive, our program actually crashes because primitive variable types can't store null. A primitive can't be null. Null is the lack of a reference, not the lack of a value. Since a primitive stores a value, it can't, bless you, it can't store null. Null is only the lack of a reference. So variables that are expected to store references can have null. Primitives cannot. So this program actually crashes. Only because I'm using int. If I use capital I integer, this wouldn't crash and X would store null. But since I'm using lowercase I int, crashes. But that's what most implementations I've seen anyway do. The Java queue, the Java stack, I should verify that before I say it, but they should not crash, but throw an exception when you try to dequeue an empty queue, pop an empty stack. Oh, that is the last slide. I was rushing the end there. We got time. Linked lists are just string theory. Yeah, let's end a minute early. It's always weird ending without music, though. Doesn't happen often, but I thought I had more slides.